Put your hand on a table. Go on. Flat. Right on the surface. Press down. You feel it, right? Solid. Hard. Real. Your hand is touching the table. Everybody agrees on that. Your grandmother agrees on that. Your dog would agree on that if he could talk. Except it's not true. Your hand is not touching that table. It has never touched that table. And I can tell you something worse than that. You have never touched anything in your entire life. Not a table, not another person, not the ground under your feet. Nothing. And I don't mean that in some poetic, philosophical, what does it really mean to touch sort of way. I mean it in a hard, measurable, physical way. There is a gap, a real gap, and nothing you do can close it. So let me show you why. Let's start with the easy part. You already know this, but let's say it out loud. That table is made of atoms. Your hand is made of atoms. Everything is made of atoms. All right? And what's an atom? Well, you've got a nucleus in the middle, tiny, positively charged, protons and neutrons all packed together. And then you've got electrons somewhere around it, negatively charged. The nucleus is incredibly small compared to the atom as a whole. If the atom were the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. The rest of the stadium, every seat, every corridor, the parking lot, the whole thing, that's the domain of the electrons. Or rather, it's where the electrons might be. Already something is strange. The atom is mostly not there. Most of it is empty space. The table you're pressing on, the one that feels so solid, it's almost entirely nothing. If you could somehow remove all the empty space from all the atoms in your body, every gap, every void, and compress what's left into a solid lump, everything that remains, all the actual nuclear material, would fit into a speck so small you'd need a powerful microscope to see it. You would weigh the same. All your mass would still be there. But you'd be invisible to the naked eye. Let that sink in for a moment. You think of yourself as a substantial thing. You take up space. You bump into furniture. And yet the stuff you're made of, the actual material, is almost nothing. The rest is architecture. It's structure. It's the way a tiny amount of matter is arranged to take up an enormous amount of room. And yet your hand doesn't go through the table. Why not? If both your hand and the table are almost entirely empty space, why can't they just pass through each other like two clouds of fog overlapping on a cold morning? That's the first real question. And the answer people usually give is wrong, or at least it's not the whole answer. The common thing you hear is this: the electrons in your hand are negatively charged. The electrons in the table are negatively charged, like charges repel. So when your hand gets close to the table, the electrons push each other away. And that push is what you feel as touching. That's electromagnetic repulsion, charge against charge, simple and clean. And there's truth to that, electromagnetic forces involved. But if that were the whole story, it would be like saying a bridge stands up because it's strong. Well, yes. But why is it strong? What's really happening? Because if all we had was electromagnetic repulsion between like charges, you'd expect the electrons to just rearrange themselves, shuffle around, find a configuration where your hand could slide right through. Charges rearrange all the time. That's what conductors do. So why can't the electrons in your hand just dodge around the electrons in the table and let you pass through? Something else is stopping them, something much stranger. And to understand it, we have to talk about what an electron actually is. Not the little ball you see in textbook diagrams. The real thing, or as close to the real thing as we can get. See, an electron doesn't sit in one place. It doesn't orbit the nucleus the way a planet orbits the sun. That picture, the one with the little electron going around in a nice circular path, that picture is wrong, completely wrong. An electron is better described by a cloud, a probability cloud. It's smeared out. You can't say the electron is right here. You can only say there's a certain probability of finding the electron here and a different probability of finding it there. The cloud has a shape. It has structure. But the electron doesn't have a position until you measure it. So when you bring your hand close to the table, what you're really doing is bringing two sets of probability clouds close together. Your electron clouds and the table's electron clouds, and the question becomes, what happens when those clouds start to overlap? This is where we get to the deep reason, the real thing holding your hand out of that table. It's called the Pauli exclusion principle, and it is one of the most important ideas in all of physics. Maybe the most important if you care about why matter is solid and why chemistry works and why you exist at all. Wolfgang Pauli figured this out in 1925. What he discovered is this: no two electrons can occupy the same quantum state at the same time. Not just the same position, the same state. That means the same energy, the same orbital shape. the same spin direction, the same everything. If one electron is already in a particular quantum state, no other electron is allowed to be in that state. Period. It's not that they repel each other. It's not that there's a force pushing them apart. It's deeper than that. The rules of quantum mechanics simply forbid it. It's as if nature looked at two electrons trying to be in the same state and said, no, that's not a thing that can happen. Now that might sound like just a rule, a regulation, something arbitrary, but it's not. It comes from the mathematics of quantum mechanics itself. It comes from the fact that electrons are what we call fermions, and the wave function that describes two identical fermions has to be antisymmetric. When you swap two of them, the wave function flips sign. And if they're in the same state and you swap them, the wave function has to equal both itself and its negative. The only number that equals its own negative is 0, and a wave function of 0 means that configuration has 0 probability. It simply doesn't occur. Nature didn't write this rule on a piece of paper and tack it to the wall. The mathematics demands it. Think of it like a hotel with very strict booking rules. Every room in the hotel has a unique number, and every guest must stay in their own room. One guest per room. No exceptions, no sharing, no doubling up. When the hotel is full, it's full. You can bang on the door. You can offer $1 million. It doesn't matter. There is no room at the inn. That's the Pauli exclusion principle for electrons. Except the hotel is a region of space, and the rooms are quantum states. Let me say it more carefully in physical terms. In classical physics, if you push two things together hard enough, they get closer. You push harder, they get closer still. Maybe they deform, maybe they break, but they get closer. With electrons governed by the Pauli principle, there is a limit. Once all the available quantum states in a region of space are filled, that's it. There is no more room. You can push with the force of a star, and those electrons will not budge. They have nowhere to go because every state they could go to is already taken. That is what you feel when you press your hand on a table. Not the electromagnetic repulsion between charges, though that plays a supporting role. What you feel is the absolute quantum mechanical refusal of electrons to share their state with other electrons. The table pushes back because the electrons in your hand and the electrons in the table are running out of available states, and nature will not allow them to double up. Think about what that means. The solidity of everything you've ever touched, every floor you've walked on, every chair you've sat in, every person you've shaken hands with, that solidity comes from a quantum rule about information. Not about force in the traditional sense, not about hardness in the way you'd think of a brick being hard. It's about the bookkeeping of the universe. Every electron has to have its own unique entry in the ledger, and when the ledger is full, nothing more can be added. I want you to sit with that for a moment, because it's strange. Forces, we understand. You push, something pushes back. Newton, action and reaction, we're comfortable with that. But this is different. This is the universe enforcing an accounting rule, and that accounting rule is what makes your chair hold you up. But wait, I said you've never touched anything. I didn't just say your electrons and the table's electrons repel. I said there's a gap, so let me be precise. When you press your hand on that table, the atoms in your skin get close to the atoms in the table's surface. Very close, on the order of a few angstroms. An angstrom is 1/10,000,000th of a meter. That's incredibly small by everyday standards, but it's enormous by nuclear standards. The nuclei of your atoms and the nuclei of the table's atoms are still separated by a vast gulf compared to their own size. The electron clouds interact, they push, they rearrange slightly, they establish an equilibrium. But the atoms do not merge. The electron cloud of your finger and the electron cloud of the table reach a point where the repulsive pressure from the Pauli exclusion principle and the electromagnetic force balance out against the force of your push, and everything stops. There's a gap, a real physical gap, between the outermost electron states of your atoms and those of the table. You feel that equilibrium as solid contact. Your nerves fire. Your brain says, I'm touching the table. But what's actually happening is an electromagnetic and quantum mechanical standoff across a tiny void. Let me put it differently. If you could zoom in on the exact boundary between your fingertip and that tabletop, you wouldn't see two surfaces meeting. You'd see two fuzzy, shimmering clouds of electron probability hovering near each other, never quite merging, vibrating, exchanging virtual photons, maintaining a frantic equilibrium. And in between those clouds, there's a region where neither your finger nor the table is really present, a no man's land, A gap that cannot be closed because closing it would violate one of the deepest principles in quantum physics. So you've never touched that table. You've come very, very close, unimaginably close by human standards. But there's always a gap, and that gap is enforced by the fundamental structure of matter. Now, where does this leave us? Somebody might say, come on, Feynman, this is just semantics. If the electromagnetic interaction between my hand and the table is strong enough that I feel it, that I can push on it, that it holds me up, then in any practical sense, I'm touching it. You're just redefining the word touch. And that's a fair point. You're right. In everyday language, touch means something perfectly useful, and I'm not telling you to stop using the word, but I think something interesting is hiding here, because the physics is telling us that contact, in the way we naively imagine it, surface against surface, atom pressing directly on atom, that doesn't exist. There is no such thing as contact in the universe. Not between your hand and a table, not between a hammer and a nail, not between two billiard balls. Everything interacts at a distance, a very small distance, but a distance. And once you see that, you start to realize something else. All the forces you've ever felt, everything from the wind on your face to the ground under your feet, are mediated by electromagnetic interactions between electron clouds that never quite merge. When you pick up a coffee cup, it's electromagnetism. When you feel the texture of fabric, electromagnetism. When you hug somebody, the warmth, the pressure, the feeling of their body against yours, it's all electromagnetic interaction across tiny quantum gaps. The only things in this universe that actually get close enough to truly touch in the sense of overlapping are things that undergo nuclear reactions. In the core of a star, hydrogen nuclei get slammed together with such violence that they overcome the electromagnetic repulsion and fuse. Their nuclear boundaries overlap. Their protons and neutrons merge into new configurations. That's real contact, if you want to call it that. But it takes the weight of an entire star pressing down on them, a core temperature of about 15 million degrees, crushing pressure from billions of tons of matter overhead to make it happen. Your hand on a table, not even in the same universe. You're pushing down with what? A few pounds of force. The electrons don't even notice. They've held up against far worse. There's one other case where things truly touch, and it's even more extreme: neutron stars. When a massive star dies and collapses, the gravitational pressure is so enormous that electrons get shoved into protons, and the entire star becomes a ball of neutrons. At that point, the Pauli exclusion principle is being pushed to its absolute limit, this time for neutrons instead of electrons. The matter is so compressed that a teaspoon of it would weigh about 1 billion tons. That's what it takes to truly get matter to touch, not your hand, not a hammer, a collapsing star. There's a beautiful strangeness to this. You spend your entire life feeling the world, picking things up, setting them down, running your hand along surfaces, feeling the sun on your skin, and every single one of those sensations is a kind of illusion. Not an illusion in the sense that it's not real. The forces are real, the sensations are real, but the picture in your head, the idea that your skin is making contact with the surface of the world, that picture is wrong. There's always a gap, a quantum gap, and that gap is what makes solid matter possible in the first place. Because think about it. If the Pauli exclusion principle didn't exist, if electrons could all pile into the same state, then atoms would collapse. Without that fierce resistance to compression, every atom in the universe would shrink down to nearly nothing. There would be no chemistry, no molecules, no structure, no tables, no hands, no you. The very thing that prevents you from truly touching the table is the same thing that makes you and the table exist at all. So the next time you put your hand on a surface and feel that reassuring solidity, that real, undeniable sense of touching something solid, remember what's actually happening. Your electron clouds and the table's electron clouds are performing an elaborate quantum mechanical negotiation across a gap so small you could never see it, governed by a rule so strict that not even a collapsing star can easily break it. And in that negotiation, in that frantic exchange of electromagnetic force across that impossibly small void, the universe creates the feeling you call touch. You're not touching the table isn't touching you, and yet here you both are, interacting, pressing against each other, neither one giving way. That's not a failure of physics. That's the magic of it. If that makes you a little uneasy, a little uncertain about the solid world around you, good. That's what physics does. It takes the things you thought you understood and shows you how much deeper they go. Let me leave you with this thought. If you could somehow compress all the empty space out of every atom on Earth, the entire planet, everything, every mountain, every ocean, every person, it would all fit into a space roughly the size of a small marble. All of the apparent hugeness of the world, all the space everything takes up, is the Pauli exclusion principle holding things apart. That one rule is responsible for the size of everything you see. So tell me, what else do you think you're touching right now that you might not really be touching? I'd like to hear what you come up with.